have this huge existing code base, which is polyglot, which means there's a bunch of implementations in different languages. It's for a 2D skeletal animation project called Spine, which is very nice. So you have an editor wherein you edit your animations, and then you have runtimes for various game engines and languages where you can load and render those animations you exported from the editor. There are implementations for many different languages like C, C++, C#, Higgs, Dart, iOS, Swift, and so on and so forth. And then there's a reference implementation in Java called spine-libgdx. This setup has been notoriously hard to test. The reason being that 2D skeletal animation consists of object graphs that interplay heavily. So you can't really unit test this. You can't just say unit test the single bone class, which doesn't make a lot of sense. You always want to test the entire machinery, so to speak. Now, writing those tests would then involve me creating a snapshot testing system where I take the object graph of an animation at runtime and serialize that out into some standardized format. And then I would like to compare that kind of serialization between the reference implementation and the implementation in C++, for example. The reason being that every time something changes in the reference implementation, it needs to be ported over to the target language implementation like C++. And those two need to basically construct and modify and update the object graph in memory at runtime in the exact same way. Otherwise, we have diverging animations in different languages, which is not good. So writing that kind of test harness that can snapshot and serialize to a standard format all the objects at runtimes or all the object graphs at runtime is a lot of work and very tedious. I have a lot of compiler engineering experience, so I know how to do this in a way that doesn't involve manually writing those serializers, but I just never found the time. And the proof is in the pudding. We have a test harness that basically allows us to visually go through each of our skeleton examples and compare them between runtimes. It's very tedious, so it would be nice to automate this, but I just haven't found time yet to do that. So recently I figured, I know exactly what needs to be done. I use Claude Code to help me write this serializer framework. And the serializer framework works like this. It's in tests, source. We first take the Java API, which is super regular, and analyze it with the Java language server. That outputs a JSON file that lists the entire Java serializer, the entire Java API as a JSON file. So it describes all the types in it for each type. It describes all the properties, the types of these properties, names, etc., etc. Type hierarchies, so super and subclasses, interface implementations, everything you would want out of a language server. So once I have this analyzed across the code base, I can then generate an intermediate representation from it, like you would do in a compiler. You take the source code and you first generate a, bytecode representation or LLVM, IR, whatever. And I do the same here. So I take this raw Java type information from the language server and serialize it out into a very simple JSON format. And I can exclude methods and types from the Java runtime that I do not want to serialize at runtime. So for example, the listeners I can register with an animation state. I don't want that, so I don't serialize get listener at runtime. Or similarly, the animation state listener itself, the type, I don't need that at runtime. But other than that, I serialize pretty much everything that's in the object graph at runtime. So let me just run this so you can better see what the outputs of those stages are. Generate serializers, basically first analyzes the Java API, then generates the IR, and then for each language runtime generates a serializer based on the IR. And the outputs it generates go into here, into output. So now we have the original language server information. So for each file in the libgdx runtime, we extract all the types. And for each type, we extract a bunch of stuff, like the fields and methods, but also superclass, supertypes, and so on. So we get the full type hierarchy here. And once we have this raw language server analysis, we generate the IR representation of this, which has everything from Java exclusions, DXD excluded, and makes it really easy to write a serializer for it. So I have, this actually doesn't serialize out types anymore. It serializes out methods that need to be written. You will see what this means in a second. So I have public methods. Those are the main entry points of the serializer. So it can serialize skeleton data, skeleton and animation state. Those are the root object types, so to speak, of the object graphs at runtime. And everything that's inside of those then gets serialized out with individual methods. So for each type, there is now a method. I have an animation type, so I have a write animation method. And the IR specifies which properties of that type need to be serialized, which can be, the property might be a getter, or it might be a direct field. Let's see. I don't know actually how I encoded this. Well, you get the idea. So basically the IR says, hey, you language specific serializer, you just need to write these methods, and within the method, you need to then access these properties and write them out as JSON, as a JSON object, so to speak. So, all right, so now we have the language server analysis of the Java API, we have the formatting, we have the IR generated, based on which the language specific serializers can now go in and translate this IR, which basically has Java method names and types, translate that to the target language. So in C++, I know the property getTimelines is also called getTimelines because our ports are very regular. And in Java, I have an array, which is an array list in Java. No, it's a libgdx array in Java. And in C++, it would be the C++ equivalent of that array. And that array works a little differently when accessing elements than the Java version. So the C++ serializer knows how to map between kinds or types in Java that are found in the IR to C++. So for example, what do we have here? Yeah, for example, array, if you need to serialize out an array, then you first, then the generated code will just use C++ loops to go through each element in the array, and if the primitive type is if the element type of that array is a primitive, then it just writes that primitive out verbatim, so a float, a string, a boolean. And if it's an object, then we know the type and can call the write method for that type. So it's very straightforward. And as you can see, the generator that creates the serializer is super tiny. There are a bunch of language-specific write methods that you need to implement for a language-specific serializer. In this case, colors are handled a little differently, texture regions, but that's it. The rest is just this very trivial generate CPP from IR method that just goes through this IR and implements all of these, or writes out all of these methods that are defined in here. Super straightforward. And obviously I also have that for Java, because we also need to write that out as well. And again, this is just language-specific boilerplate. The rest is just iterating the intermediate representation, public methods and write methods. And it's super trivial to add a new serializer for another language, because the API is pretty much the same in each language. So we just need to translate from Java idioms in terms of accessing getters and primitive types to the target language idioms. Super easy. Okay, so once I have this run that generates serializers, I do get skeleton serializer Java, which has those 3 public methods for the main types, the main entry points, so to speak, in the object graph, which then delegate to the write methods. So we have a write animation, or let's see, we have a write skeleton data, and that just goes through the properties of a skeleton data object and serializes that out. All of this is auto-generated. It's about 4,000 lines of code in the Java case. In the, let's see, oops. That's only implemented as a header file. And it's about the same amount of data in C++, a little bit more, 4,200. But you see the structure is exactly the same. We have the 3 public methods, and then for each type a write method, and they are equivalent. So let me put that side by side so you just see how regular all of this is, which makes generating this very easy. You just need the time to build the infrastructure to generate this stuff, right? And that is what kept me from doing this, because I know exactly how to do it given my compiler background, but it's just tedious. So now with Claude, I could do this in about a day, all of it, and it's fantastic. So yeah, again, here's the Java implementation of the skeleton serializer, here's the C++ implementation, and there will be a TypeScript implementation, a Hakes implementation, a Dart implementation. It all follows the same pattern. And it's great because I know there are no errors in the serializers, because I did not manually write them, so I didn't forget to serialize a property. It's all in the serializer generator. And that makes it super nice to work with, because I can trust this, which is very important. And it's automatic. So every time I change something in Java, CPP, or whatever, this is auto-generated and does the latest stuff, right? Also, if in the reference implementation we add additional properties that need serialization, this is also a way to identify that we missed porting those, because the C++ serializer is generated based on the information from the Java API. So if there is a method in the Java API that's not in C++ yet, this will generate the code that tries to access that new property. But if that property doesn't exist yet in the C++ type, this won't compile, which is also nice. So this gives me multiple validations of the port status between the reference implementation in Java and the target implementation. So right, how do we use these? Well, each runtime has a headless test class, which is very simple. It mocks a bunch of stuff because it should be headless and run on a CI. And since this is rendering API, it's more or less, we need to mock this out, but this is non-functional, so this doesn't affect anything. And then the headless test basically just takes the path of a skeleton file and its atlas, and optionally an animation we want to apply. It loads that data, and then it just uses the skeleton serializer. Where is it? Yeah, there's the serializer. It just uses the serializer to serialize the in-memory object graph for the skeleton data, the skeleton, and an animation state, which is basically how you modify the skeleton. Doesn't matter. So we output 3 JSONs here in C++, and we do the exact same thing in Java. So we have a headless test there as well. Takes the same inputs, the 2 file names and an optional animation, loads them, and then uses skeleton serializer to serialize out that data. So if we close all this, we then, as a final step, have a test runner in the test folder. Now, where is it? There. And the purpose of this test runner is, well, let me show you what it does. Up. So I say CPP, I say Spine Boy, and I say nothing for now. The purpose of this is it should compile the Java headless runner, it should compile the target language headless runner, and then run them on data, on input data. The data is specified with this short handle here. We have a bunch of projects here that we can use to test stuff, but I don't want to specify the absolute tile paths to that. Instead, I just say shortcut SpineBoy, and within the SpineBoy directory, there is, oopsie, an exports folder, and there you can find all the all the JSON and skeleton and Atlas files that you want to load for this SpineBoy skeleton. And there's a JSON variant of that and a skeleton variant of that. So the headless runner actually will test against the JSON export and the skeleton binary export, just to make sure we cover all the cases. And it's very convenient, because if I know there's a problem in the runtime with a specific skeleton that's in the examples, I can just say, okay, generate me a diff between the Java implementation, object graph, and the C++ one for this thingy, and away it goes. So what this then does is, again, compile the headless runners tests for each of the two runtimes, and then execute the headless tests with these input files, serialize out the result to JSON files, and compare the JSON files in the end. And here it already says that the skeleton data JSON and the skeleton data CPP JSON don't match. And let's look at the outputs. So we start with skeleton data Java JSON. That was the skeleton data object instance in memory loaded from the skeleton, from the SpinePro JSON skeleton file. And as you can see, it's just a serialization of the object graph in memory. It obviously has to deal with circular references, so we break the cycles in the graph. Yeah, and then comes the party trick. I have this open now, and I want to compare it with the equivalent C++ version. So in Visual Studio Code, I can just do this and select the skeleton data CPP JSON. And now I have a diff between the object graphs in Java and C++, which is very nice. There are some idiomatic differences in C++. If a property is a string, it's always a string reference, so it can never be null. Instead, the string is empty. And in Java, we have nullable annotations. So the icon, which is usually a string, if it's not given in the JSON file in the JSON we load, or the skeleton file we load, then it just sets to null. And these tiny differences obviously show up in the diff, but they are not functional differences. They're just idiomatic ways of encoding the property. There are other issues. Let's see. Yes. So obviously different runtimes, languages, compilers that will emit different floating point precision instructions, and possibly a different order of floating point operations, which aren't commutative. So we will end up with tiny floating point imprecisions and differences. And that kind of makes it harder to go through this diff, because a lot of this diff is not functional differences, but just floating point precision errors and this idiomatic difference between encoding null state, so to speak. Yeah, so you see all of this. And then there's one more thing. The property IDs, for technical reasons, are strings in Java and unsigned longs in C++. It doesn't matter for the purpose of comparing implementations what these strings or numbers are. So yeah, all of these problems, idiomatic differences like this, or the null and string stuff above, or the floating point differences, all of this the test runner can help with a special little tiny flag called f. And what this does is it will first go through both object graphs, and then if it sees that the two float values that are going to be compared are just a precision issue and not a real difference in value. So if the epsilon between those is small enough, then it will just take the Java value for that element here, for example, and write that out to the C++ value at that position. So in the diff, it doesn't show up as a difference anymore. So essentially, we're just doing epsilon testing here as a pre-processing step, so the diffs are cleaner. So now if I run this with -f, these fixes will get applied. And this is the demonstration effect. I don't know what I fucked up here. But basically these differences should go away. Maybe it's just not Visual Studio Code not updating this properly. Let's see. Compare file. Skeleton data CPP JSON. Yes, this looks much better. Okay, so this is the diff between the two files now. And as you can see, it's empty, which is very nice. Yeah, the problem is it worked. So I now know that in C++, loading the skeleton data, the skeleton files works because the skeleton data instance encodes that. Hallo, du Fabian, ich muss schnell was arbeiten. Gehst du noch kurz raus? Ich komme gleich.
Kurz raus.
Raus, ich nehme gerade was auf.
Und danke.
Danke mal. Ja? Du die.
Ich habe ein neues Buch.
Cool. Die Emily kommt heute auch, gell?
Ja?
Okay. Machst wieder zu? Ich bin gleich bei dir. Fabian, bitte raus. So. Yeah, the skeleton data is now equivalent. So we know the loading of that data in both Java and C++ is equivalent. There's another entry object type for the graph, which is called skeleton, and that gets serialized out to those skeleton state files here. And I know that there's a bug in there. So I can open this. Nope. I can't actually because I need to specify no. Somehow my terminal just terminated itself. So let's start a new one. Well, let's go to a proper terminal. So if I specify an animation at the end, it will also serialize out the skeleton object. Okay, so we get new JSON files here. Let me kill those broken terminals. And now, for my final trick, I open the skeleton serialization. Oh, I think I overloaded Visual Studio Code with those diffs. That's why. Let's see. Oh my god, now my machine is dying. Now it loaded and then it killed itself. Amazing. So let's open code up again. Yeah, there we go. So we know the skeleton data object in memory is the same in Java and C++, and now we want to check if the skeleton object in memory is the same. So we generated an additional JSON file that has the serialization of one of these skeleton objects in it for Java and for C++, and then we can compare that again. So I compare the skeleton state of Java with the one in C++. And as you can see, most of the object is equivalent, but there's a problem down here. And that problem is we have an update cache array in the skeleton. And apparently the order of objects in here is different. At this position I have a transform constraint, and here I have a bound pose, and that's wrong. So I know immediately where I need to jump into the C++ implementation. That's the code that handles the update cache, and poke at it. Or I can just take a screenshot or a textual copy of this diff between the Java and the C++ version and tell Claude to help me analyze why this is. One minor thing here, obviously the object graphs are cyclic and they need to be broken up. So objects that have been previously serialized are not serialized again, but instead we output circular here in lieu of this object. This is not super good because in this case I actually want to see all of these. I will likely special case the serializer so that it breaks those cycles only for known properties that actually recurs. Like a bone has a parent, so I could rewrite the serializer generator in such a way that every time we see a property called parent, we stop and just say, this is serialized somewhere else, or this is circular. And there's only a handful of properties in all of the types that are actually recursive or that are responsible for the cycles in the object graph. So I can enumerate them and special case them in the serializer and do this little circular trick only for them. So anyways, I could have done this by hand, all of it, writing the Java analyzer, the IR generator, and the serializer generators, and built all the scaffolding around it. I could have done this by hand, but this would have taken me probably 2 to 3 weeks. And in this case, it took me like 3 nights instead. And I have a pretty good first product, so to speak, which is super helpful. I already fixed like 10 bugs with this yesterday night in an hour or so, which would have usually taken me a day or two. This is fantastic. And this is the kind of work that Claude enables me to do, or any agentic model enables me to do in an existing legacy code base. And you should think about use cases like that, and not use cases like, build me this new feature in my fucking enterprise SAP whatever code base. No, start small. Start with these kinds of things that you pushed away for years because you knew how to do them, but you just never found the time. Now you have the time. This can help you if you know exactly what you need to do.